All right, so this is section 15.3, video number 2. So we've been doing double integrals over general regions, something which is not just rectangular. So the question might become, is it possible to do it both ways? And the answer is sometimes. It just depends. So the best idea is to probably go ahead and sketch what your D is going to look like, what your domain is going to look like. So we're going to go ahead and sketch that, and then we can make a decision from there based upon our sketch as to what this is going to look like. So let's see. The domain is bounded by y equals 0. That's the x-axis. Y equals x squared, and x equals 1. So y equals x squared, which is going to look like this, and x equals 1, which is going to look something like that. So it looks like it's the region within this section right here that we're dealing with. So now the question is it going to be better or easier to do this as a type 1 or a type 2? Part of that's going to be defined or determined, by what your surface is, whether it's going to be easier to take an antiderivative with respect to y or with respect to x first, or how we're going to deal with that. In this case, we can actually do it either way. So the way this is set up right now, you can see that you have bounds for y that go from 0 to x squared. So technically that's function to function. And then x quite clearly goes from x equals 0 to x equals 1, so that's constant to constant. So it seems like a type 1 might be the easiest way to start. So type 1, remember, is a top-down method, or a bottom to top method, however you want to think about that. So this is going to be a type 1 double integral. So let's see what we get. So we're going to, whoops, didn't mean to do that. So we're going to set up our double integral. So x is going to go from 0 to 1. Y is going to go from 0 to x squared. Our function is x cosine y, and the good thing here is that it didn't really matter because taking an antiderivative of x or of cosine of y either way would not be too difficult. And then again, this is type 1, so it's going to be dy first and then dx, because the x are the constants. So taking an antiderivative of cosine of y with respect to y is going to give me x sine y from 0 to x squared. Plugging in, oops, that should be a sine of y. Plugging in x squared, we're going to get x sine of x squared minus 0 times 0, which is 0. So we get x sine of x squared dx integral from 0 to 1. Now in this case, it looks like we're going to have to do a u substitution. So u here is going to be x squared. That's our composited piece. Du then will be 2x dx. And dx is going to be du over 2x. I'm going to go ahead and switch the bounds, I think, on this one. Again, I prefer to do that when I can. So let's see. Well, actually, switching the bounds, ironically, is going to give me the same bounds, because you plug 0 into x squared, you get 0. Plug a 1 into x squared, you get 1. So you're still going to end up with the same bounds, ironically. And then let's see. We're going to get x sine of u times du over 2x. So the x's are going to go away. I can pull the 1/2 out to the front. And then I can take the antiderivative of sine of u du. So that's going to be negative cosine. So we're going to get negative 1/2 cosine of u from 0 to 1. So plugging in 1, it's going to give me negative 1/2 cosine of 1. I don't know what that is. And then minus, plugging in 0, we're going to get, let's see, cosine of 0 is going to be 1. So we're going to get minus negative 1/2. So I think if we simplify that, we're going to get negative 1/2 plus negative 1/2 cosine of 1 plus a half. Okay, you could factor a negative 1/2 out of that, but we're fine leaving it there. All right, so that's doing this type 1. I do want to show, however, that we could have done this as type 2. Yeah, type 2. So type 2 would be going this direction, from left to right. In order to do this as a type 2, however, all of my functions, x has to vary from function to function. So really what that means is I have to solve this one for x, because we know x is going to, looking at our function, we know x is going to go out to 1, but it's going to start at whatever this thing is in terms of x. Well, that's pretty easy. That's going to be x equals the square root of y. Notice I don't need the negative square root of y there, because in this case, the region does not go to that part of the square root of y. It doesn't go into the negative values. So we can now do a type 2. All right, so let's see. Y has to go from a value to a value. It's going to go from the smallest y value, which is down at the x-axis, that's 0, to the highest y value, which is that intersection right there. When x is 1, so is y, because that's the point 1, 1. So y is going to vary from 0 to 1. And then x is going to go from 0 to the square root of y. Again, looking at the function, the x values go from 0 up to the function. Excuse me. I think I have that backwards, actually. That is completely wrong. Ignore what I just said. It actually goes from the square root of y, because that's the leftmost piece, out to 1. That's the rightmost piece. Okay, there we go. All right, our function doesn't change. It's still x cosine y, but now it's going to be dx dy, because the y part varies from constant to constant. All right, so let's see what we get here when we go ahead and finish this one off. Antiderivative now with respect to x first is going to give me 1/2 x squared cosine y evaluated from the square root of y to 1. Let's see, I can pull the 1/2 all the way out to the front. And plugging in a 1, remember we're plugging this in for x, is going to give me cosine y. Plugging in the square root of y squared is y, so it's going to be minus y cosine y dy. Don't forget the integral. All right, so in order to do this one, we are going to have to split this integral. So it definitely looks like type 1 was shorter, but it's important to see that you can do this either way. So I'm going to split this, so we're going to have 1/2 of integral from 0 to 1 of cosine y dy. That one will be pretty simple. Minus the integral from 0 to 1 of y cosine y dy. So the first one, the antiderivative, is relatively simple. That's just going to be sine y from 0 to 1. That one won't be difficult to do. This second one over here, you might think let's try u substitution. If I let u equal y, however, it's not going to get rid of that extra y. So this one, because it's a product of two things, and we can't use u substitution, your next thought process should probably go to integration by parts. Remember, there are multiple ways you could do integration by parts, but considering that y is a terminal derivative and cosine of y is cyclical, I'm going to use the tabular method. So here's my u, here is my dv. So u is y, dv is cosine of y. Remember, we take the derivative down the left-hand side until it terminates, so it'll be 1 and then 0. We take the antiderivative on the right-hand side, so the antiderivative is going to be sine of y, and then it should be negative cosine of y. We match these up to multiply. Remember, we keep the sign, change the sign, keep the sign. It keeps alternating. So ultimately, let's go ahead and rewrite this. As a matter of fact, let's just go ahead and finish off this left integral. So I'm going to get 1/2 of sine of 1 minus the sine of 0, which is 0. So we get 1/2 sine of 1. So 1/2 sine of 1 minus. Now we're going to do the integration by parts over here. So that's going to be y sine y. Change the sign here so it should be plus cosine y. And we'll evaluate that from 0 to 1. Just double checking to make sure that looks right. I believe that that is correct. All right. I don't think I made any mistakes there. So we get 1/2 sine of 1 minus. Now plugging in 1, I'm going to get 1 sine y, which is sine, 1 sine of 1, which is sine of 1, plus cosine of 1 minus 0 plus cosine of 0, which is 1. Yeah, I think that's good. And if I'm not mistaken, I did make one mistake, one big mistake here. I did not bring the 1/2 through all of this, because really there should be a 1/2 distributed to all of this stuff. So let's do it this way. There, that looks right now. All right, so inside the double bracket there, it looks like I get sine of 1 minus the sine of 1. That's gone. I'm going to get a negative cosine of 1 and a positive 1. So I'm going to get 1/2 times negative cosine of 1 plus 1. And if I distribute that 1/2, I'm going to get exactly the same thing that I did on the other side. So they do work out. This type 2 in this case was definitely more difficult as far as the antiderivatives. Not horrible, you just had to remember your integration by parts. Okay, let's move on. So this one says evaluate this particular double integral, and it actually gives us the bounds by reversing the order of integration. So it's not as easy as just saying, okay, let's do dy dx, and we're just going to change the integration bounds, to make the y squared 9 on the outside and the 0 and the 3 on the inside. Because remember, your constants have to be on the inside. So what we really need to do is we really need to figure out, what does this thing look like? Okay, and you should be able to actually figure the domain out by looking at the bounds. So let's write down the way it is right now. Right now, your x is on the inside. So x varies from y squared to 9. So we can write that down. X is going to be in between y squared and 9. And the y part is going to go from 0 to 3. So 0 is less than or equal to y is less than or equal to 3. Okay, that's the way it stands right now. So what does that look like? Let's sketch that. Well, y goes from 0 to 3. We won't worry about that part yet. X is going to vary from function to function. So x kind of tells us what we're looking at. X is going to go from y squared. X equals y squared is a sideways parabola, and it's going to go from there to 9. So the sideways parabola part looks like this. And it's going to go from y squared, from that function, out to x equals 9, which is a vertical line which looks something like that. So that would be 9. This would be y squared. Y, however, is bounded from 0 to 3, which means that we are only talking about this region up here. So really that whole bottom part we can get rid of. We can kind of ignore it because y is only bounded from 0 up to 3. And the 3 part makes sense because if you plug 3 into y right here, you're going to get x equals 9. So it does make sense that that intersection right there is y equals 3, x equals 9. Okay, so we're going to write that now. So to reverse the order of integration, this was a type 2. We're now going to put it into a type 1. So we're going to make it so that it's going in this direction as opposed to left to right. So what is y going to vary from? Well, we have to solve this part right here for y? Well, that means y would be the square root of x. So y equals the square root of x is going to be the upper bound for y. And then the bottom bound for y is just the x-axis, which is y equals 0. So we're going to have y equals 0 and y equals the square root of x. And then x is going to go now from constant to constant, which is going to go from here to here. So 0 to 9. So x is going to vary. Oops, that should not be a 0 there. It should be an x. From 0 to 9. So now we can actually write this as our type 2 and, our type 1 now, and reverse the order of integration. So let's see what we get. dx has to be on the outside. X now goes from 0 to 9. dy has to be on the inside. Y goes from 0 to the square root of x. We're going to have y cosine of x squared. Now it's dy dx. And the question is, why would they have asked us to reverse the order of integration? We'll take a look at this. Take a look at the original function. In order to do that thing with respect to x, first I'd have to know how to take the antiderivative of cosine of x squared. Well, we don't really have a good method to do that. We could, we don't want to, we could go back to series. Probably don't want to do this when using series. That would be not so fun. So reversing the order of integration here is definitely our best bet. All right, now that we've reversed the order of integration, we should be able to complete this pretty easily. So we're going to take the antiderivative with respect to y first. So let's see, that's going to be 1/2 y squared cosine of x squared evaluated from 0 to the square root of x dx. So plugging in the square root of x, I'm going to get 1/2 the square root of x squared, which is 1/2 x cosine of x squared. Plugging in 0 for y, I get 0. Now we can do this with a relatively simple u substitution. U will be x squared. Du is going to be 2x dx. So dx is going to be du over 2x. All right, so let's see what we get now that we've done the u substitution. So I'm going to change the bounds. We're going to have, let's see, 0 to 81, plugging in the 0 and the 9. We're going to have 1/2 x cosine of u times our new du, which is du over 2x. The x's will go away. The 2's are both in the denominator, so I can't cancel those out. As a matter of fact, it's going to give me a 1/4 on the outside. Integral from 0 to 81 cosine of u du. Antiderivative of cosine, of course, is sine. And we'll evaluate that from 0 to 81. This is really not going to be a nice number here. Let's see, that's going to be 1/4 of the sine of 81 minus 1/4 the sine of 0. Fortunately, that's 0. So 1/4 the sine of 81. And there is our answer. And again, we had to do that one by reversing the order of integration simply because we wouldn't be able to figure out how to take the antiderivative of cosine of x squared without probably going back to infinite series. Again, probably really don't want to do it that way. All right, I think that is plenty enough for this particular video. Again, we'll come back with one more video. We should be able to finish it off in one more. There.